Welcome back to our lecture series in STA211, Probabilities 2. Today we are going to be talking about conditional probability, independence, and Bayes rule. It is noted that we require every possible outcome of a conceptual experiment under study can be enumerated by us as statisticians. There are so many conditions that are attached to probability, to events, which eventually update our probability value. In this course, at the end of this lecture, you should have been able to explain what is meant by conditional probability, what it is all about, and discuss the concept of independence and Bayes rule. Let's say, for example, that two dice are rolled, and we are interested in the probability that the sum of observation that comes up after this throw exceed 8, given that one or more of the faces is a 6. So when we look at situations like this, all right, there are different ways through which conditionality has affected or is meant to affect the outcome of our results. Conditional probability requires that events A and B that are associated with sample space are defined in such a way that event A is obtained given that B has already occurred. Having said that, conditional probability is written in this format: probability of A given B equals to probability of A intersection B divided by probability of B, and probability of B must not be equals to 0. And this is how we specify conditional probability. Going forward on this, let's take an example. In an experiment of tossing two coins, we want to compute the probability of 2 heads giving a head on the first coin, the probability of 2 heads giving a head at the first coin. Now, the first thing we need to define here is our sample space. Sample space. And the sample space here for 2 toss of coin is head, tail, head, and tail. And since we have this, we have to define event A. So let's say A equals to head, event that head occurs on the first coin. Okay, so if you look at head occurring at the first coin, we have this, we have this. So the set will be head, then head, tail. All right. Now, event B is such that head occurs at the second row, and that will be head, and tail, head. Having written this out, it becomes very important for us to be able to obtain our conditional probability. Don't forget, we already said probability of A given B equals to probability of A intersection B divided by probability of B. So the first thing we want to do is, what is A intersection B? Now, A intersection B here will be what? Will be a set of head. Okay? And if we have to quantify this as probability, don't forget we have written this out all as events, but now let us write them as a probability value. Now, it means that the probability of A will be 2 over 4, which equals to 1 over 2. Probability of B is also 2 over 4 because there are 2 events in B, and we have 4 listed in the sample space. 1 over 2. Then probability of A intersection B equals to 1 out of 4, which is 1 over 4. In order to compute the conditional probability here, using the formula that I have specified above, and that is probability of A given B equals to probability of A intersection B over probability of B. This will be 1 over 4 divided by 1 over 2. Okay? And if you do this properly, this will be 1 over 4 times 2 over 1, which is 2 over 4 which equals to half. So the probability of A giving B in this example is what? Is half. Now, and that's the concept of conditional probability. Now, let's quickly move to independence of two events. If event A and B are independent, then the conditional or unconditional probability are the same. And the conditions that are required for A and B to be independent are as follows. For example, for me to show that event A and B are independent, I must have been able to show that probability of A intersection B equals to probability of A times probability of B. It means that if multiplying each of these differently gives me the same result with this, which is probability of A intersection B, then I can conclude that A and B are independent. And how does this affect conditional probability? For example, if A and B are independent, all right, don't forget conditional probability specify that probability of A given B equals to probability of A intersection B over probability of B. Now, if A and B are independent, it means that probability of A intersection B can be expressed as probability of A times probability of B divided by probability of B, which can cross out, which equals to probability of A. So, independent of events makes probability of A given B to be equal to what? Probability of A. And the way to manage this is such that you understand. Oftentimes I always tell students, when we are looking at probability of A given B is what will inform what your denominator will look like. So under conditional probability, if my interest in probability is to obtain probability of B given A, okay, this will be probability of A intersection B divided by probability of A, because now I'm interested in giving A. So this is very, very important, in the context of independence of two events. Now, let's look at an example here. Let's say, suppose that we throw a fair die 2 times. Okay, we throw a fair die 2 times, and we say event A is the event that the first throw shows a 5. So I say shows a 5. Okay, and event B is the event that the second throw shows a 3. Shows a 3. The first one is say first throw shows what? First shows a 5, second shows a 3. Now, the best way to compute the sample space in this environment, because we are talking about 2 die, is for you to write the die out. 1, 2, 3, 4, 5, 6. That is the number of faces that a die has. Then we have the second one, 5, 6. Then you can start multiplying 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Okay? Now, because this helps students to gain speed, especially during exam, the interest is the first shows a 5. So I look at which one is the first. All right? The first is here. This is 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. Okay? That is my interest. Then we said the second, all right, shows a 3. So that will be 2, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3. Okay, so the first showing a 5 is here, and the second showing a 3 is here. Both of them, they have 6 elements listed. So this will be a probability of A in this context will be 6 over 36, and for B is also 6 over 36. And how do we obtain this 6? Is just by counting the number 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3. That is when we have 3 on the second row. Okay, then having 5 on the first row, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. That is also 6. Okay, now the context is to clearly state whether A and B are independent. For us to show A and B are independent, we need to first of all obtain probability of A intersection B. Let me first of all write A intersection B itself. I have only one, which is a 5, 3. That is where A and B coincide in this experiment. All right. So now if I'm interested in the probability of A intersection B will be this 1 over 36, whereas probability of A is 6 over 36 and probability of B is also 6 over 36. So for me to prove whether A and B are independent, then probability of A intersection B must be equal to probability of A times probability of B. So, and if I do that, this is already 1 over 36, then 6 over 36 times 6 over 36. Okay, that is what we need to show. Okay, so if I were you, I will first of all divide them. This is 1 over 6 times 1 over 6. Okay, and this is 1 over 36. All right, so proved. So it means that since probability of A intersection B, which is 1 over 36, equals to the product of probability of A and multiplied by probability of B, okay, then we can conclude here that A and B are independent. Now, having said that, it is also very important that you understand that we are talking about 2 events. So what happens if we have 3 events? Let's say we have A, B, and C. If we have A, B, and C, the conditions that we are to satisfy for us to be able to conclude that event A, B, and C are independent are more compared to when we have 2 events. Now, when we have 2 events, all we needed to satisfy is the probability of A intersection B equals to probability of A multiplied by probability of B. Okay? But when we have 3 events, we have to satisfy the probability of A intersection B intersection C equals to probability of A multiplied by probability of B multiplied by probability of C. Then we have to go to the pairwise combination. Probability of A intersection B equals to probability of A multiplied by probability of B. Then probability of A intersection C equals to probability of A multiplied by probability of C. Then probability of B intersection C equals to probability of B multiplied by probability of C. Okay, now if we are interested in testing whether A, B, and C are independent, 1, 2, 3, 4 conditions have to be satisfied before we can conclude that A, B, and C are independent. But if only these 3, I mean, probability of A intersection B, probability of A intersection C, probability of B intersection C that are satisfied, but this is not satisfied. I mean, the probability of A intersection B intersection C is not satisfied. Then we conclude that A, B, C are simply just pairwise independent. That they are just pairwise independent. Okay? They are not independent, but they are just simply pairwise independent.